There we go. Hey everyone, welcome to Astroveo's Coast to Coast podcast of science, astronomy, and the world around us. My name is Joseph, he's David, and we're just two friends who happen to be professional astronomers with a deep love of telescopes, astrophysics, and all things science. We checked earlier today. We are not AI yet, so this podcast is going strong. We've got a great show for you today. We're going to be talking about a topic that we know is of great interest to many people, the interstellar visitor 3I Atlas. What is it? What do we know about it so far? And of course, is it aliens? Now, David, you've been hearing many stories about 3I Atlas. Have they converted you into the rest of us, a believer?
Yes, this is gonna be the world's shortest podcast. It's aliens.
Aliens podcast over. No science required.
Well, so is it Marv the Martian? Is it the little green guys from Independence Day? Probably not.
You don't have to go that specific.
Oh,
It's
no.
not very scientific, David.
Oh,
We
in
need to
that case,
test the
what is it?
hypothesis.
It's
Aliens?
just a hypothesis. Okay, so is it little green men? Is it blobs of primordial ooze in spacecraft? Probably not.
It's obviously the rock that seeded Earth with life. I think it's pretty clear.
Okay. That atmospheric river that hit California yesterday must have, or a couple of days ago, must have really sort of put some stuff on your house.
I had to do a lot of shoveling.
Yeah, the stuff coming at you now. Oh god. Anyway, so I'd be very interested to hear your opinion as well. But I think we can reasonably safely say there's no evidence that it is aliens. I think in our fantasies it might be, or if you can see some stuff online which you think, well, maybe it's pointing to that. But I think if you, especially as you and I are actual real scientists with PhDs in astrophysics, I think we can actually then talk it through the scientific method and come to the conclusion it probably isn't.
Yeah, my take is pretty similar. Um, you know, this isn't aliens technically, but there's a really interesting correlation between over the last century or so, or last 50 years or so, reports of Bigfoot have plummeted. And this is really interesting because people have been carrying around phones with cameras more and more. And so you'd think that if Bigfoot was real, and so I actually think there's a really interesting parallel here, which is, um, we're getting more and more, what are the odds that we're getting so many interstellar objects? And well, actually, we have more and more of these amazing surveys that are happening, as we go along. And most recently, of course, is Rubin, which is literally designed to discover these sorts of things to amazing levels of detail. And so we're gonna find a lot more of them. So for a lot of people, it's like it's new, it's exciting that we've discovered another interstellar object, but actually they've been flying around. We just haven't caught them.
Yeah,
And
I think that's
yeah,
100% correct.
and that's a way I think to separate sort of like is this a Bigfoot kind of thing, aliens kind of thing, or is it like a science kind of thing? And the more cameras we got, the more we're seeing these things. So it seems like it's a science kind of thing. So my for this one only, I reserve judgment for future. My bet money would be on not aliens as well.
I agree. Yeah, that's a big caveat for this one only, and also more data may change our minds, but the
That's true.
data currently
We have to keep it open mind.
open mind, absolutely. But I think I really like some of the things you said there, and I've got a couple of young friends that I speak to up there in Washington State up there in the Arcadia Mountains. Ethan and Nora, hello if you're watching.
I
These
I know.
these are two of my wonderful friends. One is 11 and one is 8. Nora's 8. And they asked some pretty interesting questions, and I did tell them that I was going to do this podcast with you, so they're super excited. And one of the questions they asked, and it's sort of related to what you said, is you keep using the word interstellar instead of solar system, and so really they want to know is where did it come from, and how did we even detect it? And you talked about these astronomical surveys. What does that really mean?
So sorry, I got distracted halfway because of your shoulder angel.
Oh, my shoulder
Actually up again. Yeah, yeah.
Yeah, if I move my head, which way do I have to move my head? Oh, there it is. So this photo in the background is the Blanco 4-meter telescope in Chile. I'm obviously standing in front of the telescope, but now it does look like
The shoulder angel. It's just I need to know because there's only one of them. Is it the evil one or the angel one?
Well, like all things in life, there's a little bit of both. Depends
Right,
on
so
your point of view, by the way.
the jury's out on the sorry, could you ask the question again?
Okay, so what are you
I'm
doing?
covering the shoulder angel.
Are you covering my shoulder?
Yeah.
This is the good one.
Focus. So I can focus, David.
You, you've got to concentrate, concentrate,
Yeah.
concentrate. Okay, so Ethan and Laura want to know what is the difference between interstellar and, say, solar system? What does the interstellar part mean? And how did we even detect Three Eye Atlas? And by we, I mean astronomers. How's that related to the astronomical surveys that you mentioned earlier on?
So, the first question but those are both incredible questions. So, there we have a
Well,
solar
they're not
system.
incredible children, by the way.
Honestly, you told me a little bit about them. They sound utterly remarkable. Um, so, we have a solar system, and the solar system is effectively objects that are gravitationally bound to the sun, so they orbit around the sun in some way. And objects that originate in the solar system and then orbit around the sun in some fashion, these are solar system objects, and they're part of a class of objects that we understand relatively well because we have so many examples of them. We are very interested in objects that are not solar system objects. So these come from outside the solar system, and these are called interstellar objects. And the reason we're particularly interested in them is because they are likely to not be like anything we've ever seen because specifically they don't come from the system that we're most familiar with. This is really exciting because we like it when our established rules get broken. I know there's a sort of perception that science likes to be right all the time, but every scientist I know is most excited when the thing that they thought they knew was really wrong. And interstellar objects are a great candidate for that. And so that's like the distinction there. And the way we can tell an object is interstellar or not largely comes down to its orbit. So there are three types of orbits. There are bound orbits, and they're basically categorized by their ellipticity. So there's bound orbits, which are objects that just orbit the sun. And then as the orbit gets more and more elliptical, so it has more and more closer and closer to a sort of escape velocity, you get to the parabolic orbit, which is when the ellipticity is exactly one. And this is an object that's teetering on being a bound object versus unbound. And then if the object is fast enough, and this can happen if usually if it's coming from outside our solar system and only briefly passing by, it has a very high eccentricity above one, which is pretty much just you can imagine like a huge ellipse that we're in a tiny corner of, and this is called a hyperbolic orbit. It's not quite elliptical, but it's like it comes in like a hyperbola and then comes out, and then goes out. And so, if an object comes in and
So
measures
to quote Miley Cyrus, "You came in like a wrecking ball."
exactly, exactly. She was thinking about hyperbolic versus bound
Hyperbolic
trajectories.
interstellar objects.
Yes. Well, actually, is the maybe the wrecking ball is not actually that bad. No, no, it is. I don't wanna make a claim there. I was gonna make a claim about the tension on the wrecking ball tracing out a parabola, but that's actually not. I think it's too. Yeah,
Yeah,
that's
no.
too much. Yeah, it's too much. Too much. So, but yeah, so that's how we tell. We measure the orbit and we see, okay, is it what's the shape? And if it's hyperbolic, we know it probably originated from outside of our solar system. And if it's not, then it's likely just bound to the sun at least for a very long time. The question of how we discover them is really interesting. So we have these surveys that scan the whole night sky every couple nights, and they take an image from. They'll take a picture on Monday, and then they'll take another picture on Wednesday of the same spot, and they'll subtract them or compare them side by side, and they'll look for anything that changed. And anything that changed is called a transient or a. Is there another word for it, or does transient just for specific
Heard it.
transient? Right? Yeah, yeah.
It's transient.
So anything that changes in the night sky is a transient, and then they'll catalog it. And at that stage, we don't know what it is. If it's moving on the sky, it's probably some sort of object that's very close to us because objects that are far away tend to be fixed in position. But if it's just fixed in position, it could be any number of things. It could be stuff like it could be a variable star that's just fluctuating in brightness. It could be an active galactic nucleus spitting out a big flare, or it could be a star getting disrupted around a black hole, like a TDE, a tidal disruption event, or it could be what I study, supernovae, a star exploding in another galaxy somewhere. So we're really interested in things that change in the night sky, and oftentimes, actually, a huge amount of the time, they are planetesimals or rocky bodies that are executing orbits. In fact, when Rubin turned on, which is Rubin's going to be a discovery engine for these kinds of things, within the first 8 hours, they found like was it 2,000 new asteroid-like objects that had never been seen before in any catalog, and that's just the first day it turned on. So yeah,
I think it was I think it was over 10,000 actually. It was a huge number.
I think it was 2,000 in the press conference that they
Oh,
did, which was the
2,000.
preliminary. Yeah, yeah. But it was breathtaking to see. It's like just they're all over the place.
I think in the lifetime of the survey, they're talking about detecting and characterizing, I think between 6 and 10 million new solar system transients.
It'll basically map out everything that Rubin could see, which is a lot, and that's just in the southern half of the sky. Um, I don't know the numbers for asteroids, but like for supernovae, you're expecting literally millions of new
Oh,
supernovae by the time the survey ends, which is unbelievable. It's going to change everything. But yeah, so I hope that answers the questions.
it does, and I'm actually gonna you actually defined it really nicely, and I'm gonna put it into, much simpler terms, shortly. So can you show me you have, I know you prepared a really nice graphic for the surveys.
Yes. So
Let
this was
Yeah, while you're putting that image up, let me perhaps answer the question, those questions maybe in 10 seconds instead of the detail that you gave. So the big difference between interstellar and solar system objects is interstellar is an object that came from outside the solar system for the reasons you said. And by the solar system, we mean anything to do with the sun. Yeah, that's that hyperbolic or
football.
parabolic orbit you're talking about there with that little dot is going to be the sun.
That's correct.
So basically, everything we can see inside the solar system is bound by the gravitational force of the sun. These three known interstellar objects, yeah, like that, like a planet or a comet, that looks like a cometary orbit. These three interstellar objects that have been discovered, including the latest one, 3I Atlas, are objects that came from outside our solar system, presumably from another sun like system elsewhere in the galaxy.
Mm.
And then to go to the second part of it is these astronomical surveys you're talking about, these transient surveys, these synoptic surveys, essentially, as you said, they take photographs. We're calling them photographs, but these days they're digital images. And they take them, say, on day one, and then they take them on, say, day 3 or day 5 or day 7, sometime later. And as you say, you compare the two and you see what changes. And the two types of transients you see are the things that change in brightness, and you described that really well, the type of transients that you see, or things that move. Now, while the background stars and galaxies do move, and of course Earth itself is moving, you have to take into account Earth's motion, those objects are so far away we don't see them move, at least not typically in days or weeks. But the things that do move tend to be things like solar system objects or very nearby objects such as the so-called high proper motion stars. They're objects so close to us, we actually do detect their motion in fairly short timescales. So I think you're about to show us the images of how 3I Atlas was discovered that Ethan and Nora are so interested in finding out.
Yeah, so to sort of this is an example of 3 Atlas, but of a different object. This is a supernova that I wrote a paper on. We used Atlas to discover it, and basically, what you're seeing here is an image that was taken before the supernova exploded. That's this image over here before, and then sometime after. And what you can see is that the stars are these black dots, and you can see that they stay in exactly the same position. I've blocked them out so it's easier to focus on the object, but at this exact position, there was nothing, and then after some point, there was clearly something. And when you, subtract these 2 images, you're left with just a lovely little blob in the middle there that shows you something new. And surveys like Atlas or Rubin do this for the whole sky that they can see for every little part. And it looks kinda easy to tell here, right? I mean, you can tell by eye there's clearly something there. So why is this such a hard problem? Well, here is the discovery image from Atlas. And what you can see is the region that this is 3I Atlas, that little dot there, and it's from this tiny region of one of the densest and most brightly populated parts of the night sky. It is an incredibly, incredibly challenging problem to detect these objects. Detect this tiny little dot that moves from here to like over here over the course of a night. And this is the real discovery image from, Atlas. And, because Atlas discovered it, that's how it got its name. 3I refers to it being the 3rd interstellar object I, and then Atlas it's, the discovery engine, which was the asteroid terrestrial last alert system, which lets Earth know when there's nearby objects. But it also picks up everything else, like supernovae and interstellar comets or interstellar objects.
Just
So
out of interest, by the way, Joseph, this is the exact same technique, this difference imaging, as how Scott Shepherd and Chad Trujillo find these new moons of the outer planets. And we
that's
have talked about these two people before, and they do these very, very nice surveys where they're looking for near Earth asteroids, asteroids in the solar system, but also they discover new moons around things like Uranus and Neptune. And so that's the exact way they do it. They're looking for moving objects.
this technique is used so many places, supernovae, asteroids, but also how the Kuiper Belt objects were first discovered was via
Okay.
difference comparisons like this. It's such a powerful technique, and it's really exciting whenever you see something in the sky because we often perceive the sky, night sky, as being basically unchanging, with the exception of the planets and the moon. But actually, it's alive with a lot of stuff, and it's so exciting to think that there's stuff happening out there on our humble human timescales.
Absolutely. Well, just to continue the thought on this, and we didn't well, we addressed it slightly at the beginning. Nora, my 8-year-old friend who lives out in Snoqualmie, she asks a very intelligent question. What do we gain what does humanity gain out of studying objects like this? Like sort of what who cares?
Mm. Do you wanna try start answer that first? Maybe I feel like you have a much, I have some thoughts, but I feel like you have a much, sort of,
Okay, yeah.
more advanced
So again,
perspective. Yeah.
a very intelligent question. I mean, we're talking about Ethan and Nora, 11 and 8 respectively. These are very intelligent
Is
questions.
Ethan Zora, it will be a loss to humanity if you 2 don't become scientists.
Oh yeah, no, I don't know what Ethan will end up doing. I hope he does become a scientist, but Nora's definitely going to become a scientist. She's phenomenal. Um, so that's a very good question. Why? I mean, it's sort of why do we study astronomy at all? Who cares? And I think what it really is, and I think this is probably the reason why you and I became astronomers and astrophysicists, is it's somewhat addressing the need of the human condition to learn about our surroundings and our origins. Because we do look up in the night sky and it's not static. We do see an awful lot of things that change, including with our own eyes. The most obvious being the sun and the moon change both their position and brightness very often. But we do see planets move and we see stars twinkle and we see that stars are different colors. And I think early cave people thought, what's going on? Why is it like that? And I think that's the origin of astronomy. Now, there were obviously some cultural and religious aspects that came into it over time, but I think the fundamental questions that we want to answer is what is the nature of the universe and what is our place in it? And so I think by studying objects like this one, especially the fact that it doesn't come from our solar system, it comes from another star system, I think it starts if we can understand those type of objects, then perhaps we can understand the objects in the solar system, ultimately understand the place in which we live. And I think that's a big driver in why any of us do astronomy, actually.
I love that. I love that. I totally agree, David.
Great. So then, Nora, that was a great question. We answered that directly for you there.
There's a I think there's an additional perspective on this, what I think you could draw directly from Carl Sagan and from, Self-Reliance by, Waldo. Ralph Waldo Emerson? Wait, that is, right? The author of Self-Reliance? I forget, yeah, okay, thank God. Carl Sagan said that, human beings are a vessel for the way for the universe to learn about itself. And so, in some sense, I think that the study of science as a whole is part of a larger, cosmic duty that a lot of us feel because we are, as Carl Sagan said, star stuff. But then also, there's the flip that sort of Emerson pitched in Self-Reliance, which is that the exact opposite is true as well, which is or the corollary, which is the learning about the universe is tantamount to learning about ourselves, because the same rules that govern everything we see in the sky govern us at the highest and lowest levels.
Yeah.
And, there's a deep, there's a deep satisfaction that I think a lot of scientists have when they're learning about the universe and discovering something new, and I think it traces back to the deep, feeling of I am learning not just about the universe, but about who I am and where I belong.
Excuse me. Yeah, I couldn't agree more. And I think it maybe I don't know if it's always been this way. Maybe you and I were like this as teenagers, and my children are like this now. And I see it in society where we always want to be right and we always want to tell people we know stuff. I think one of the greatest pleasures and drivers actually of being a scientist is actually to say, I don't know. Like, oh, I wonder why that tree grows like that. I don't know. But you know what? I'd love to find out. Or I wonder why the stars twinkle. That's what I thought when I was 7. That's got what got me into astronomy basically is why do stars twinkle and why are they different colors and why do some stars appear to move? Of course, they were planets, right? I just didn't know. I think that,
Unbelievable.
yeah, right.
You didn't know their planets were ridiculous.
But that fundamental response to I don't know is I wonder why.
Yes.
And I think that gives me the greatest joy of being a scientist actually, is actually when I don't know the answer and I have to then think about what could be the answer.
Yes. And when you're with other people who have that sort of same mindset, it's like
Yeah,
one of the greatest privileges. It's
it's a
like
privilege. It's a
it's a real
complete
privilege.
privilege.
I love that. That's a great question.
Yeah, no, absolutely. Like I
Yeah.
said, that's why I love these two kids that I know through this family friend out in Washington State. They ask some fundamental questions that I think I asked myself as well when I was their age. And I think children are really good at asking questions of a fundamental nature because as adults we get encumbered by our jobs and our families and having to pay bills and the car needs an oil change and I think it's hard to think of deeply about things.
Mm.
But when you're a kid, you've still got that joy of life. You haven't got the pressures of going to work and oh god, I've got to get up and change the baby at 10 o'clock and all that sort of stuff.
I really believe in the idea that scientists are just children who write things down. Like,
Yeah, no,
they're just big
absolutely.
kids, like,
Yeah, we're big kids. I mean,
there's a childlike wonder when
it is.
you have the
That
permission
childlike
to
wonder. Yeah,
yeah.
absolutely.
That's why Threat Atlas is so exciting to everyone. It's like it's a it is, it's very it's similar in a lot of ways to comets and asteroids you've seen before, but it's also anomalous in new and exciting ways, and that is always an opportunity to go, "What new can we learn?" Like,
Yeah,
what more?
right, what new can you learn?
Yeah.
Yeah. Uh, so, do I think I can see this. I don't know if our viewers can see this, but I think we have the discovery, some more close-up discovery images
Yes.
of
So,
this.
not quite Discovery images, but here's a close-up from Hubble. Uh,
Unique of it.
yeah, it's beautiful. David, why are these looking like, little earplugs?
Well, I was going to ask you the very same question. Now, I think what is going on here is that Pac-Man was late,
Mm.
was coming after this big dart, and so this is Pac-Man zooming across the screen, which of course is utter silliness. So I'm going to stop that right now.
I don't think I that seems like a very vacuous answer, David. I think clearly these are the probes released by the mothership to explore Earth.
I mean, we should. I was gonna say we shouldn't joke about this, but we actually should. One of my favorite movies of all time, by the way, was Close Encounters of the Third Kind. It was 75 or 76, and it was Richard Dreyfuss and that big spacecraft, and they did the noises, the doo 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 doo. Oh God, I loved it. Um, anyway, getting off topic. This is a very cool image because the telescope that took this, Hubble, was actually doing something quite rare in that most of the telescopes we all use in astronomy track objects, be them stars or planets or galaxies. Um, yeah, well, planets are slightly different. Let's just say stars and galaxies by basically counteracting Earth's rotation or the motion of the spacecraft if it's in space. And it holds the object stationary where the images look in focus. And so what you see is you see stars and galaxies in focus, and you see the normal star and galaxy patterns that you see in all the images that Hubble has produced. What Hubble has done in this particular case is done something called non-sidereal tracking. At least if it was on the Earth, Hubble is not in the Earth. Obviously, it's orbiting the Earth. But the Earthbound telescopes, they basically counteract the rotation of the Earth. Well, to observe anything that doesn't isn't very far away, like solar system objects, you have to have something called non-sidereal tracking. And what that means is you focus the tracking, the mechanical tracking of the telescope on the object you're looking at. Exactly. In this case, it's 3i Atlas. There it is. Now that's it. Its motion is going somewhat strangely across the stellar sky. So, compared to the background of stars and galaxies, its path is somewhat unusual. So, if we were focused on, say, the stars or the galaxy, the telescope would, all those little tic tac like dashes that you said, they would appear like stars. And it would be 3i Atlas that was smudged. But we want to see 3i Atlas in focus. So what Hubble did is it turned off its normal star tracking system. It has a couple of little telescopes that focus and gyroscopes that keep the platform stationary and stable. And what it did was it actually tracked the motion of the object itself. And so it is in focus. And these tic tac like objects are stars that are not in focus and are slowly drifting across the image as it took its exposure.
The beautiful explanation. It's also worth, bringing back to the discovery image of this object, which I don't have here, but one of the things that got people really excited about Thread Atlas was of its conception tied to this sidereal tracking issue. When, Atlas discovered 3 Atlas, but I think Rubin was the first one to advertise it because it showed up in their first light images, and,
Really?
yes, but Rubin does not sidereally track. It just takes a picture of the sky, or rather, sorry, it does sidereally track. It was not tracking 3i Atlas. And so as a result, it appeared elongated. And not only did it appear elongated, it looked blue and then green and then red because that's the colors of their filters, and 3i Atlas was sort of streaking through it. People were like, "This is clearly a rainbow spaceship." Like, 'cause it looks like a little pill capsule with multiple colors in this beautiful image the
It's the
Sagittarius.
Skittles mothership.
Exactly. And so that was like the inverse problem. And so it looked like these stars here.
Yeah.
But when we wanted to do real data and take real observations and do science with it, we track the object and not the sky, as David said. Um, we while we're on images of 3 Atlas, one image that I didn't add here, but I'm gonna add now because it's so freaking cool, is this is one of my favorite images. Uh, do you know what this is, David?
I do believe if I was to take an educated guess that that is an image taken from your balcony.
No, that would be awesome. No, this is an image of 3i Atlas captured by Perseverance on Mars.
No.
Yeah, isn't that so cool?
Oh my God.
Oh, wait, sorry, I lied. That's the Mars
No, that
orbiter.
can't be true because it wouldn't be able
It
to keep focus on the comet or
no, no,
the object.
you're right. That's Mars orbiter. Yeah, sorry, that's the Mars orbiter. I was
Oh,
close.
Mars orbiter.
Yeah, there is one of it. Um, there is one of it from one of the rovers. There is one from one of the rovers.
Really? The
I
camera's
think
that sensitive?
yes, it didn't look great, I recall. This is it. This is the Perseverance rover camera. I'm gonna get rid of this. That was cool also, super cool, but this is the one I was thinking of. I'm so sorry. This is from the Perseverance rover camera. Why does it look so poo-poo?
Oh my God.
It came out super low resolution for some reason. Um, I got this. Sorry. We're doing this live, folks.
No, no.
I am screenshotting NASA. There we go. Yeah.
Screenshotting that.
So this is from the Mars rover. And it's just I just think it's so cool.
Well, you do know that, and I think you know the answer to this, but taking photos or astronomical images from the surface of Mars has an awful lot of advantages over taking images from the surface of the Earth.
Because of the thinner atmosphere.
A much thinner atmosphere, so you don't get the blurring and seeing effects that you get here on Earth.
Also, throughout Atlas passed quite close to Mars, which is one of the anomalies.
Yeah.
We'll discuss that more later, but it did have a better view of it than I think we did. The Earth-based telescopes did.
Yeah, no, absolutely.
I just think this is like the coolest thing ever.
That's phenomenal. I didn't know
Right.
it had a powerful enough camera. That's amazing.
Yeah, it's so cool. Yeah.
This must be a long exposure image though, because it is smeared.
Yeah, it's long exposure, and, I think that there's some processing going on to make it as bright as possible, because normally a good picture is not gonna have this sort of noise, And so they clearly are boosting it as much as possible to bring out Victoria Atlas. Yeah. But yeah, I just thought that was so cool. So we have some other stuff that we can chat about. What strikes your fancy, David? We can talk about JWST images, photometry, spectra. Uh,
Let's I really do like the JWST images actually.
okay.
So what's the difference? Here's a question then. I think we probably know the answer between us, but so what's the difference between the JWST and Hubble?
Um. Do you mean technically or like the obvious answer, which is that they're different telescopes?
Well, okay, they're clearly different telescopes.
What's the difference between me and you, David? Are we even different people? That's a legitimate question I've asked myself.
Well, we have different people, but
We're very similar.
no, seriously. What's the
But yeah, sorry. So yeah, so well, for JWST, interestingly, people think JWST is a lot more powerful in terms of resolution than Hubble. It's not. I think it's the resolution increase is like 5 or 10% or something like that. The difference is JWST, unlike Hubble, which was mostly optical and near infrared, JWST is a far infrared telescope, I believe, like or very infrared focused, and that lets us see through dust that was restricting a lot of Hubble's view. It also has a cabal of extremely sensitive instruments, much better than anything Hubble had, particularly an array of spectrometers. And it has a very different design. Hubble was a standard school bus sized cylindrical telescope with like a circular mirror, whereas JWST has broken into many sections, hexagonal sections that give it a very unique diffraction pattern.
That's true. I think if memory serves, I think Hubble a 2-meter telescope and 2.4 meter, and I think JWST is a 10 meter.
Let me
Right?
double check on it.
Am I remembering that correctly?
Uh, Hubble Hubble mirror size. Hubble's mirror is yeah. I'll copy this picture from ESO. Hubble is a lot smaller than GWST. But my understanding is the resolution is not that much better. That's correct, right? Like I don't think the angular resolution. This is the difference in the
Oh, yeah,
kind of.
yeah. I think it's 2.4 and 10 meters.
So the angular resolution of Hubble is like around 5 hundredths of an arc second. And then JWST is, yeah, about the same. So they both are around a tenth of an arc second.
That suggests to me then that JWST is faster and Hubble is slower. I wonder if
That would affect depth. But
and resolution.
okay.
It,
So
but yeah, it does
wait,
it affects resolution.
wait. I hope I don't lose my job over this. What I understand is resolution is from the Rayleigh criterion. You have wavelength over diameter of the collecting area. So where does the exposure come in? Or are you just talking about from the software perspective, like you can super resolve with a lot of extra
No, no, it's but well, the resolution comes into it, right? Because a fast telescope has a lot lower resolution, but it's collecting more photons per unit per unit
oh,
resolution element. So you need less exposure time, which is why it's called a fast telescope.
um,
But you have to factor in. Don't forget, it's not just the primary mirror. You have to factor in the secondary or tertiary optics as well.
okay.
So you don't.
I'm not sure I totally agree. I think you're talking about like a general trend, which is that like if you have a telescope with a very large collecting area, it can be uh it collects a lot of photons and also has a higher angular resolution. Like because I think that I don't think, for example, it look like let me put it this way. The different telescope designs, as you know, have different collecting power. So like a 6-inch Schmidt Cassegrain will be way slower than a 6-inch Roe Ackerman, for example. They'll have the same but because they're the same size and both observing optical, it should be the same angular resolution, but certainly one will be a lot faster than the other.
And it's to do with the secondary and tertiary optics.
Oh yeah, I agree with that. I totally agree with that. Yeah, like for example, if you wanted to make my 6-inch faster, you would add like a focal reducer, which is a tertiary optic. What I mean is though, like in terms of what the resolution of a telescope is, it's not really connected to how much right? Like
No, it is. That's what the F number gives you here.
okay.
It's yeah, no, it definitely is. So I mean, if to resolve this, I think if you were to look up the F number of the systems, not just the mirrors, I think what you said in the beginning about the Rayleigh criterion is correct.
Okay.
But I want, but these must have similar final F numbers for the.
Okay, JWST's F ratio is F20. Hubble's F ratio is F24.
Yeah, there you go. They have pretty okay, so they're actually
Okay.
both quite slow, but the which is why they have high resolution.
Okay, I see. Interesting. Okay. That
But
that was the thing. Yeah. Mhm.
yeah, so and also they tend to have narrower field of views, and that is they're both that's true for both of the Hubble and JWST telescopes.
I do see where my confusion was now. I was thinking solely about how resolution and photon collection rate is affected by the primary mirror size. You're talking about secondary, tertiary optics. That makes total sense.
Yeah, yeah,
Yeah.
the sort of delivered image quality, the DIQ as it's called. Yeah.
Okay. Delivered intelligence quotient
Well, for me and you, that's like 3.
combined.
Come on. What you're 2.8 and I'm 0.2.
No, 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 no. Nice try. Okay. So, yeah. So this is these are images from JWST.
Yeah, right. So these look like these are in these the XY axes are basically position or index, so they are just showing you the like a positional map. And the left hand one is from the integral field unit. The that's an infrared. 4.3 microns, that's also infrared, and then 2.7 microns, that's sort of near infrared.
Yeah, but this is kind of different. You're kind of focusing on different elements here, right? Because this is if this is IFU, this is going to be like sort of all wavelengths, and then this is going to focus on CO2 and then
Oh, the
water.
picking up a CO2 line and a water line. So
Yeah.
this actually shows quite nicely that while there is a water signature coming from this object, there's actually quite a big, what looks like a CO2 halo around it. And then when you go to the integral field, which must be just a broader wavelength distribution, you're seeing this really large halo of distributed material.
Right.
Uh,
The
so definitely, it does have a water signature, though. That's very interesting.
yeah, it's got a bunch of water, and the coma is pointing directly away from the sun, as you can see here. It's showing the sun direction, and I think
Yeah,
this is the comma V is also it's saying it's the direction of its velocity, right?
yeah, I think so.
Okay. So, David, can you explain to us what these are and why there isn't one over here?
Yeah, yeah, I'm just I think I'll see if I can see it. These are essentially sort of mini spectra. Essentially, you're looking at the amount of light coming through on the y-axis, and on the x-axis, you're talking about wavelength. And you can think of wavelength as sort of the colors of the rainbow when you see a rainbow in the sky. And so around these wavelengths, the central peak, you're seeing a lot of emission. That's what these peaks mean. And the central part of this emission corresponds to one of the, what I suspect is either rotation or vibration of the carbon dioxide molecule. And it's taking place at 4.3 microns, where microns is 1 millionth of a meter. And then the right-hand image, again, you're seeing either probably, again, rotation, I suspect, and rotation and vibration, or even thermal emission of water. And in this case, it is at 2.7 microns, so about half the wavelength of the carbon dioxide molecules. And so these are what Joseph and I would call spectra, but essentially this is sort of flux against rainbow color.
And this is one of the things that JWST is like that people were really excited about was this IFU instrument because effectively when David and I work with spectra, usually we're working with something like this, where it's just you have a thin slit across an image, and just in that slit, this is how the brightness varies with wavelength, and you can look at these lines. But what JWST can do is it can give you that spectrum, like that for every single pixel in the image, effectively. And so you can look at not just what elements are in the image, but exactly where they are occurring. And that's what this map over here is showing. There's some spots where the water isn't as prevalent. That's extremely interesting.
Yeah, absolutely. Yeah, the fact you're seeing water and carbon dioxide right near the nucleus is actually very interesting.
Yeah.
And presumably, and I haven't studied this object in that much depth, but presumably there's a lot of outgassing of any volatiles as it approaches the sun and warms up, as a typical comet would do. But this, I think we'll discuss this shortly. But this is clearly not a typical cometary-like object.
Mhm. There's referring to the outgassing, we can quantify exactly how much of what the emission we see is outgassing, or rather the coma versus just just convolution due to the resolution of the telescope. And so stars are point-like objects, and so you can measure the fall off that they experience as a function of radius from the center, and that's what this blue line here is. So any object that's just a true point will follow effectively something like this, depending on its brightness. But then 3i Atlas clearly does not follow this trend. It has a excess emission above even what you'd expect from the low resolution, and that's an indication that there is stuff around it. And
So it's
of
big,
course,
big
yeah,
and fluffy, basically.
right. And you can see that there is it's big and fluffy, and the fluffiness is dependent in direction. There's a spread on how fluffy it is, and it's very fluffy in the direction along its path, or along the vector connecting it to the sun, and not as fluffy perpendicular to that. And that's a very good sign that the puffiness we're seeing is due to volatiles on the surface being heated up by its proximity to the sun
Exactly.
and ejected.
Yeah. And just to be clear for the listening audience here, that the volatiles tend to mean things that are easily evaporated.
Mhm. Things that are quick to anger.
Yeah, that's right. Yeah. They're very angry substances that evaporate very quickly.
Yeah. So I really like this plot from the VLT showing that. Do you think is a nice segue to talk about the spectra then?
Yeah, absolutely.
Okay, so we have this JWST spectrum, in addition to the H2O. So we were looking at a zoomed in view of this and this line, and I believe this line. And you can actually see because in the previous figure, those lines were at 4.3 microns and 2.7 microns, which is exactly where we see them here. So we were looking at specific elements, but you can see there's a lot of stuff. So can you tell us, David, about what else we're sort of seeing in these figures?
Yeah, this is actually I've not seen this spectrum before, but super interesting.
It's
So
weird, right?
I know it's
Is
amazing.
that there a ton of
Well,
suppression in the red?
there's a huge amount of science going on here. So you can see that there is, again, on the y-axis, it's flux, which is sort of amount of energy or amount of brightness, amount of photons. And the x-axis is in wavelength, and again, that can be, yeah. So you can think of the electromagnetic. Exactly, that's exactly it, as Joseph is showing you there. And so this part of the spectrum, this from 1 to 5 microns, this is near infrared essentially.
But can humans see this?
Say that again, please.
Can humans see this?
Could I what? Sorry.
Just for the audience, is this part of a spectrum that humans can see?
Oh, sorry, I misunderstood. No, human eyes don't see this. We need special detectors to see this. Our eyes stop working actually just off the left edge of the graph. Our human eyes work between about zero point 0.4 microns and about zero point 0.7 microns. So way off the left edge of the graph, and we see a very narrow region. So the rainbow that you see in the sky going from red to blue, red is about zero point 0.7 microns and blue is about zero point 0.4 microns. So we see a tiny part of what would be this graph here.
This is kind of in the range of where like a thermal camera would see, right?
Yeah, no, absolutely. Yeah, almost everything coming from here is normally due to thermal emission or absorption. Yep, absolutely.
It's kind of cool. We're like looking at through Atlas with like night vision goggles.
Yeah, no, well, that's so depends on the type of night vision. Night vision goggles tend to be image
Uh,
intensifiers, actually.
Thermal night vision goggles.
Yeah, thermal, yeah. Well, those are pretty rare, and yeah, the military have them, but they're not really.
David's drawing on his extensive experience in MI6.
Well, I was dyslexic. It was QH4, but
What spectral line does that correspond to?
I don't know, a corium or something. I know.
David knew Welshium.
Welshrian there. I'll take that. Yeah, there you go. Welsh Star Warsium. Yeah, so you're basically seeing amount of light against wavelength here, and it's really interesting. So this part, the very near infrared part where it says dust scattering, what essentially this is almost certainly due to incoming radiation from, say, the sun, and there's an awful lot of dust around the coma, the very sort of the nucleus, sorry, the very center of this object, and dust is really good at scattering light. And you can tell it's scattering because the line is essentially flat. Now it's going up and down, it's peaking at about 1.2 microns. But the fact it's flat does suggest scattering because there aren't any, no, not flat like that, Joseph, flat as you go along, as you trace it along.
Oh, you mean like this?
Yeah,
I
and
see.
what it doesn't have these big emission lines like the CO2 line, the carbon dioxide line at 4.3 microns, or even these water lines at 2.7 microns. The very fact it's flat suggests there's no wavelength preference. So any incoming radiation just gets scattered in all different directions, and so you end up seeing wavelengths from all when you see emission from all wavelengths, and so that's why you don't see any emission lines. They've all just been scattered out into a continuum, which is what a continuum is, what we call it when you just see flatness.
Here's
So
here's a fun dust question for you, David.
yes.
So in this spectrum, dust is causing emission. Why is it that dust will instead sometimes cause absorption instead?
Sorry, say that again, please.
In this spectrum, dust is causing an emission sort of feature here, like excess flux. But in a lot of other spectra, dust causes absorption. It reduces or reddens spectra. So why do we see emission here and absorption in other systems?
Yeah, that's a good question. I'll have to think about that a little bit, see if I can come up with something scientifically sensible. So dust typically absorbs.
For our viewer, these are the kinds of questions we like to think about, even if we don't immediately know the answer. It's fun. It's like a fun puzzle to think about. Phenomena that we see.
Um, so so I don't I don't know from this graph that I can give it a formal answer because I don't know if if there's been any background subtracted. So I don't know whether this is emission per se or just completely scattered solar
I
radiation.
I don't think this is subtracted because this is showing clear continuum features, and then this is the subtracted
Mm.
right here.
Oh, I see what you mean. Yeah, I see what you mean. Huh. I have to.
By continuum features, I mean, so any object that has a temperature on a plot like this with flux versus wavelength will emit what's called a black body spectrum, and then the lines that you see live on top or below it. And so when you see this kind of overall sweeping behavior, that indicates there's some sort of continuum or background black body going on.
So is it to do with the fact that the dust is being heated up as well, and so its black body temperature is just way higher,
Yeah.
where
That
interstellar intergalactic dust is very very cold?
That's what I'm thinking. I think that you have an object that is surrounded by dust that is being illuminated by light from the outside. Whereas for objects that will have dust absorption, you have an object where there's dust, it emits light and then gets scattered in the dust, and then that light has to reach the observer. And so I think this is where you get the absorption, and then this is where you get reflection,
I see. So the cartoon you drawn on the bottom is actually a,
like a supernova.
absorption basically an absorption spectrum, which the one we're seeing here on the left hand side, the dust scattering, is actually a reprocessing spectrum.
Well, reprocessing can be, absorption as well. Yeah, I think reprocessing fair to say. Yeah, reprocessing is
Yeah, I think there's just a massive amount of reprocessing going on here. Also, that just I mean, this may I don't know if this is related to it, and like I said, I think the real answer to this is I'm not sure, and I'd have to think about it a bit more. It's a great question, by the way. Is I think the flux coming from the sun, the flux of infrared light coming from the sun, is really, really high. With a standard infrared flux or any flux of any radiation going through just interstellar and intergalactic space, and then when it hits dust, is quite low, unless it's say in a star forming region or something like that. And I wonder if just the sheer amount of flux has something to do with it as well.
okay. I like
I
that.
don't know. If I'm being really honest, I don't know the definitive answer.
My guess would be a combination of, like, you have this overwhelming amount of infrared light, and then also, dust is really bright. Like, dust is super bright because it interacts with light so easily, and that's why it'll absorb the light of something coming from inside of it because the interaction cross section is so high. But, if you have, photons, like, reprocessed by the dust and then emitted, there's nothing to stop them. They don't get reabsorbed by the dust again at the edge. But let me put it in perspective in this way. I think that we see an emission spectrum from the dust, but if you had an observer on 3-eye atlas, they would see an absorption spectrum from the same dust.
Yeah, 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 I think that sounds right as well. I think there's also just and this is just for me and you, and not this is a bit, maybe a bit too technical for our general viewers here, is I think there's an optical depth thing going on here as well. With a standard, the amount of dust you would see in interstellar intergalactic space doing the absorption, uh, you could have 5 grains per cubic centimeter, or
Mm.
10 to the 20 atoms per cubic centimeter. Here, there's just the sheer quantity of material and the closeness or the amount of radiation it's receiving from the sun. Like I said, probably just ends up raising the temperature, and you're seeing an awful lot of thermal emission here.
Mm. I like this process that we're sort of engaging here of we're not exactly sure about something, and so we're testing our own knowledge by trying to make a
Yeah,
prediction and
right.
comparing things we see. That's really at the core why, uh, you know, it's really easy if somebody shows you the spectrum and you come up with a reason for why it looks like this. But if you have it's harder if you come up with a reason and then use that to make a prediction about something else that you've seen, and then this lets you test whether your hypothesis is really valid. And that's why, like, you know, kind of bringing it full circle, it's easy to look at the anomalies of this object in hindsight and say, "Oh, can't explain it. Must be aliens." But actually, like, you shouldn't. The prediction becomes the hypothesis becomes more strong. It's a beforehand prediction because then you're sort of constrained by this scientific method and what we were and David and I were just kind of engaging in right now.
Yeah, absolutely. And I really like that observation too, Joseph. You're 100% right. Is that sometimes even when you don't know the answer, the quickest path to, oh, they're aliens, is not necessarily the right one, and it's not. It sort of defeats Occam's razor of it's the most simple solution is probably correct, and jumping to aliens is not the most simple solution for something.
It's arguably too simple of a solution because, like, the nice thing about aliens is that, like, we see all the we David and I see all this spectrum, we go, "Oh, that's weird, that's interesting." With aliens, you don't know what technology they have. You could invent anything to explain away these features.
Yeah, that's right.
And so, like, the alien hypothesis has a lot of explanatory power and almost no predictive power for the same reason. Um, so yeah.
Yeah,
Thank you for coming to my TED Talk.
One yeah, one thing to note, by the way, and I just wanted to point this out, it just occurred to me actually, is the spectrum on the left is actually from JWST, this orbital platform in space.
This is a separate
On
one.
the right are terrestrial. They're from the VLT, the Very Large Telescope, which is a sort of a group of four 8.4-meter telescopes in northern Chile. And these data are produced using X-shooter and UVES, which are uh, optical infrared spectrographs. So there's actually a big difference between the spectra on the right here and the spectrum on the left.
It's pretty much this is a zoomed in view of this region. Um,
Yes, but by different instruments.
by different instruments, yeah, but they should, give relatively the similar spectral lines, different SNR, different sensitivity curves, but if the data or the spectrum being processed properly, there should be a high degree of consistency between them, right?
Well, they should if they were taken at the same time, yes.
Oh, yeah, I do think these were similar times, but that's a really good point, yeah, they could be at very different times. Um, yeah,
And also the resolution of the ones on the right are clearly very much higher than the one on the left.
yeah, resolution, and it looks like maybe, exposure.
Yeah, I can't tell what resolution is, but getting high resolution in the infrared is difficult.
Mhm.
Of course, the one on the left here, of course, was taken without Earth's atmosphere, so you don't get the effect of all the basically water molecules and hydroxide molecule sort of doing all the absorbing.
Whether it's resolution or exposure, it's just a much higher SNR spectrum. Over a very broad range too. JWST is kinda OP.
Oh yeah, no, amazing. One thing that's very interesting to me as well here is that there's a couple of regions on the left-hand spectrum there, where it says H2O ice.
Yeah.
And so you've got this huge absorption dip at about 3 microns.
Mhm.
And it's so this is presumably a water ice that, like we know here on Earth, that's surrounding this object and perhaps on the surface of the nucleus of this interstellar object. And the very fact there's this big dip here that Joseph already explained, there's massive absorption going on. of sunlight at about 3 microns. So the water molecules here, or the water crystals, are absorbing all that infrared light coming from the sun at about 3 microns. And just the sheer breadth of it must mean it's incredible just the quantity of material that must be there. Uh, and then but then you see all this other, continuing on the between 4 and 5 microns of water ice as well. And you can see there's some absorption, as well with these superimposed, emission lines of carbon dioxide and, carbon monoxide. But very, very interesting that there's so much absorption going on from the water ice at the nucleus.
What's really crazy is even though, like, as you said, this is a huge amount of absorption, like, for anyone who's familiar with spectra, this is an enormous feature. What's really interesting is this is, one of the anomalies about the 3-eye atlas is that it has less water than you'd expect for a comet.
Yeah,
Uh,
but
this has been invoked in some of the alien hypotheses, but I think that it's been a little bit misleading to people because they hear, "Oh, comets have a lot of ice, and 3-eye atlas doesn't have any ice, whereas its water must be a spacecraft," but it's actually we're quibbling over values here, but, like, we've detected or I think the coma is around 4% H2O, and that corresponds to an estimated, active surface deposition of, like, 30% water,
yeah.
and that's a little low for a comet, which is usually more like 50%, but I'm gonna need more than a 20% 20 percentage point gap there before I start saying aliens. It's I mean, we have a drought out here in California. Maybe there's a drought on 3 Atlas T.
An atlas sprout.
Exactly. This is clearly just bad water management.
I know. There's actually another beautiful scientific point here, and it's actually some to do with chemistry. Have you noticed that there's this massive CO2 emission feature at about
Did I notice it?
4.3? I know it's the biggest feature there, right? Like 4.3 microns. There is a subsidiary emission feature at about 4.4 microns. It's still carbon dioxide. Why is there a secondary absorption peak?
Okay, so if it's, at a different wavelength, that's an emission feature at a different wavelength, so it's gonna be a different chemical configuration. The, electrons are in a different orbital where they'd absorb a different wavelength, of light, or sorry, they'd emit a different wavelength of light when it's stimulated, would be my
Yeah,
guess.
that has to be true, of course, but it's actually a different chemical species. If you notice, it says 13
Oh, yeah, right
CO2.
there.
So the primary peak is due to standard carbon, which is carbon 12, mass number 12, atomic number 6. This carbon molecule, these carbon molecules are absorbing infrared light from the sun and reprocessing it, vibrating rotationally, row vibration model modes, and then re-emitting it. That's what the emission is, but it's not standard carbon dioxide. It's 13,6 carbon dioxide. So this is the 13,6 is an isotope of carbon. So it's actually a slightly different chemical species. Even though the element carbon is the same, it's an isotope of the 12,6 carbon.
That's extremely cool. That's a great eye too. That's a fantastic catch.
Yeah, no,
So it Yeah, sir?
no, sorry. I was just sort of saying, yeah, I sort of noticed that. I'm like, why the heck is there a subsidiary peak there? Like, oh, it's 13,6 carbon.
You see this quite a lot, elemental lines in spectra will often have 2 or sometimes even 3 peaks. Um, what's an element that has calcium the calcium triplet, right, in a supernovae spectra it'll often have 3 peaks that correspond to is it different species or is it, um,
No, it's the
different
same.
transitions, right?
Different transitions. So the calcium peaks, it's actually ionized calcium. It's calcium 2. And the calcium infrared triplet, it's at sort of near 8,500 angstroms. I can't remember the exact wavelengths now. It's been a while since I've seen those. It's the same. It's ionized calcium, but you're seeing transitions between, say, N3 and N2 or N4 and N3. So there's a triplet line there. Yeah.
Yeah, so this is a good look into the spectra. So, yeah?
Hang on, I may be questioning myself here. That might not be true because I'm thinking of something like the Balmer series where you go from n equals 3 to n equals 2. But is that true? N4. I think that's right. I think the infrared triplet are three different transitions. I can't remember the exact transitions, but it is ionized calcium.
Mhm.
Yeah, because there's also a calcium. Uh, is it calcium two? Yeah, it's calcium two H and K lines in the blue. So I think they are different transitions.
Okay. Yeah, so this is gives you a good idea of how scientists use spectra to get an insight about like the chemical composition of the object and how we know what we know about Pure Atlas at all, which I think is always really cool. And
Absolutely.
so we've talked a bit about the elements that make it up, and now an interesting question is how does this compare to other comets? And so I found this figure showing the production. So one of the things that was like to bring it back to the alien thing, because I know this is a question that a lot of people have about like is it an alien spacecraft? Why don't we think so? Why did some people think so? One of the things that people claim they had a very anomalous nickel production rate, and the claim was we were seeing so much nickel because it was a nickel plated spacecraft. Um, which is in of all the ideas I've heard, that is one of them. But this is a comparison of nickel production rate of 3i Atlas, which is in blue here, as a function of distance from the sun, compared to sort of all the other comets that we know about, or some other comets. And so, to my eye, it sort of immediately looks like it's producing quite a bit of nickel, especially far away from the sun, but it's not, it's on the upper end, but it's not so anomalous as to be it's like a 2 sigma anomaly, it's not, "This is a spacecraft anomaly." What do you think looking at this plot?
Yeah, and I agree. I mean, I think I'll be careful that the object isn't producing nickel.
Sorry, yeah, the nickel we observe, via the spectra.
Yeah. So which one is it? That's there it is. Three. Where's three I Atlas? I can't.
Sorry, 3 Atlas is this, set of
Oh,
observations.
is this set? Yeah. I mean, first of all, it's got it does show sort of like a range of the amount of nickel that you're seeing. Um, and I think what is essentially happening is you're actually seeing different parts of the nucleus. Perhaps sometimes it's being obscured. What's the range? What's the there's actually so this is a log graph. So there's actually about a range of about a factor 10 here. Well,
It's clearly varying significantly with, distance.
it is varying significantly with distance. I'm also wondering if I wonder if it's to do. Is it being is nickel is it being produced? So that's the thing I'm not sure about this graph is when it said produced, is it being produced because it's being struck by the solar wind or cosmic rays, and it's changing an element into nickel? Is it picking up nickel from the solar system, or is it the nickel it itself has? That's what I'm not sure.
I think it is, um, I don't that's a good question. Um, that's a good
The,
question. I think it is
these are
I think when they say "produced," they mean sublimating off the surface. Like, produced as in the comet produces it into the coma, like, it's the material is
oh,
there, and then it gets liberated.
yeah. It seems there is a function of heliocentric distance, so that means how basically how far away from the sun it is. This is clearly one of the closest objects. Although that is odd because if they were are all these other data points comets or comet?
Most of them are. So, the green ones are these are Borisov, which is an interstellar object. The, red ones are, I think, comets in the or like, getting gravitationally trapped by Jupiter, and then these are Oort clouds, so, like, very far out. And then, this is Halley's Comet, or Halley family.
Yeah.
And then these are I don't know what external comets means. Um,
What's the word?
it says a external comet, semi-major axis greater than 10 to the 4 astronomical units. So this is very far out.
Oh yeah, so these are probably all cloud comets or yeah.
Well, the yellow ones are Oort cloud.
Oh,
So I think it's like a separate distinction. Like maybe they come close or something.
oh
Um, yeah.
So I think there's a couple of one of the biggest thing, or two, there are two big points about this graph. Firstly, all the comets have there's quite a large distribution here. So you can't say that a given group of comets has a set value, right? There's a
Yeah.
spread in all of the cometary families. But one thing to remember here is this is a comet or a comet-like object. And we're not sure it is a comet yet, but a comet-like object that has come from another stellar system. So, and we don't know the composition, the fundamental composition of that stellar system. So it could be non-sun-like. So it may not have the metallicity that looks anything like our sun. It could be, for all we know, metal poor. So
But
it's very
I think it's key to note though that even in this sort of anomalous case, it's still the nickel production is still not unusual for
correct.
comets on
I think that
on the whole.
yeah, I think you're 100% right. It is the data are not inconsistent with the other nickel production values of other cometary-like objects we see in our solar system.
Oh,
So
I
I
just
think
thought of a fun way to put it. This comet's not winning. It's weird, but it's not winning any Guinness records, Guinness World Records.
no, 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 you wouldn't say, "Oh, we should pay attention to this because its nickel content is extremely odd." Sort of not really. It sort of matches the distribution pattern of a lot of other solar system-like comets.
It has an interesting trend with distance from the sun. That's certainly a little bit
Yeah.
unusual. Yeah.
Yeah. But I think a big difference here is as well, one could argue that 3I Atlas is now the most studied comet with modern instruments and telescopes.
That's going to inherently make it anomalous because we have just the ability to, yeah, see more. Yeah.
Yeah, and a lot of inner solar system comets, the ones that so see this heliocentric distance here, the ones that come really close in. So what does that say? 4AU on the left hand side. That's inside the orbit of Jupiter. Once comets get inside the orbit of Jupiter, they don't. The smaller ones don't last very long. They also don't hang around. They don't stay in the sky that long because, of course, they're coming to the fastest part of their orbit, depending on their eccentricity. And the ones that we know have studied well, like Halley's Comet, for instance, we haven't had a chance to measure with very good quality instruments because I think last time Halley's was here was 1986 or something like that. And so this graph was quite sparsely populated for us to make any sweeping statements, I suspect.
Yeah. I'm in strong agreement. It's like I said, it's the best studied comet ever. If you like took this graph and then just flattened it into a distribution, uh, 3i Atlas would be sort of firmly living in it and not a strong outlier.
Yeah, no. And I think
So
you
yeah,
mentioned sorry, you mentioned something really interesting about this comet or this comet-like object, I should say, is that and you see this, of course, in a lot of the sort of newsreels and all these like all these YouTube videos that talk about aliens and advanced technologies, and it's got some weird behaviors. It may well have some somewhat weird behaviors that we can't necessarily explain easily. I think what a large part of that is that the data that we're observing and its characteristics don't fit well-known models that we have. But scientific models, A, are not always correct, and B, they may not be relevant for this type of object, especially given it's an interstellar object, not a solar system object.
it's
And
certainly
that's
bold to say this object is anomalous when we only have two other objects that are anything
yeah,
like it.
it's such a small group. And I think one thing to be careful of, even if you're a non-scientist, but you're well read, but especially if you're a scientist, you don't want to be jumping to the alien conclusion straight away because there could be 1,000 other explanations. And while we have observed this object with some pretty high powerful telescopes, some great instruments, some good scientists have done some really nice work on this object. We've only known about it for about 6 or 7 months. Well, I can't remember how long it was discovered ago again, but it's certainly in the last year. I think you have to be very careful to say, "Oh God, Independence Day has come true. It must be this," or "It's War of the Worlds and the Martians are going to invade," based on its nickel abundance, or its rotation period is a bit strange, or it's got some anti-tails, or it's got various properties. Yes, it's some of its properties are a little bit different from comet-like objects we're used to seeing. Some of its motion is somewhat interesting. It has come from another stellar system, so it isn't exactly like the sun system. It's also been on this journey through the galaxy for God knows how long. It's
Who knows what it's
possibly
picking up?
possibly millions, maybe even billions of years. It may have interacted with all kinds of environments and had its fundamental properties changed. So you will be really careful to say, "Oh yeah, there's this object that doesn't look like solar system comet-like objects. Yeah, it must be an alien. Marvel Martians coming down. Yeah, this is really exciting." I think it's much more sensible to say, "Oh, look, this has got some interesting properties, and by the way, we actually know nothing about its history. We have sort of no sense of what's going on at the very center." And that's true of a lot of solar system objects, by the way. There's plenty we're still learning about the solar system, even the giant planets. They're revealing new things to us all the time. So I just want to be, I love the fact that we've been a bit laughy and jokey on this podcast about this object, and we're talking about Martians, and it's got all these wonderful properties. You and I have got we love Star Wars and Lord of the Rings. We love fantasy ads, but you have to be careful that you separate fantasy from scientific fact. And to say, hey, we've got this some data that look really interesting. Got it, yeah, it could be aliens. Oh, but we don't have enough data to say it isn't. Um,
That's where the area where things are disprovable is fundamentally science needs disprovability. Like, if you're not working with something that is a provably false hypothesis, then you're not doing science, you're kind of just engaging in speculation. But I also wanna, like, add to that, um, there's certainly a perception that scientists love being right so much that we'd rather deny that it's aliens than admit we were wrong. But I can promise every dear viewer, every listener, that if there was anything in this data that indicated there was anything even close to aliens, David and I would be the first ones to trumpet it, and we would be the most famous scientists of all time. Like,
oh yeah,
it's the hard thing to resist that urge to be like, "I want fame and attention," and, like, "I wanna be the guy that discovered aliens." It's not even a bad thing to want that. It's not a bad thing at all to want to be the famous scientist who discovered the first aliens. Like, that's a totally natural thing, but you have to resist that urge and sit down and say, "Could this be anything more plausible?" But that's not coming from a strong, like, "We have to be right, and we said it wasn't aliens, so it can never be aliens." It's coming from, like, we don't wanna, it's coming from a, "We would love it to be aliens, but we also want to say true things that we can back up reliably."
yeah, and keep the public faith in scientists that they are doing they're being rigorous and they're being careful with the tax dollars that we're being given to do this kind of work. And I think there is a very strong distinction here as well. Now you study supernovae, right? And you've done some really exciting work recently on putting together some models of how certain supernovae work and so on. If you get that wrong, the very worst that can happen is your reputation suffers a little bit and you have to go back to the drawing board and you think of a new model to explain the data. In this case, this isn't just a mathematical model that's not working and you have to then think of new ways of trying to prove your observations correct. If there were ever a group of either some objects or a group of observations that showed an object was capable of being an extraterrestrial civilization or technology, that would be arguably one of the biggest discoveries in humankind.
It would be the biggest. Like, what?
Probably the biggest since
Yeah.
possibly the biggest ever. Now, again, I'm leaving things like religion out of this, and but of the physical sciences, it would be by far the biggest impact on humanity ever. So, if you're gonna advocate for it, this type of object or this type of anomaly or something in science you can't explain, being something of so fundamental, of a magnitude that's so fundamental to the way humanity views itself and its place in the universe, you better be right.
Mhm.
Because otherwise, you've basically just got 8.4 billion people saying all scientists have no idea what they're doing because they promulgated this idea of, yeah, Marv the Martian was correct and little green men are going to invade. And hey, those that Independence Day movie was completely right. Oh my God. If you don't get it right, then all science looks ridiculous because the very first, the first doubters are going to say, why didn't you check? And I think you're right. You and I, if we produced a video about this object and said it was Martians, we'd get a million hits, and you'd be the next big internet sensation. But you've got to be rigorous, and you've got to be honest with yourself and say, yeah, am I going to sleep tonight if I say these are aliens? Nobody can prove me wrong right now, but it's about being, having that sort of discipline to say, as a scientist, I might be wrong. I better check this.
I would go even farther to say, like, can I sleep tonight knowing nobody can prove me wrong? It's not as a scientist, I don't find much joy in making a not undisprovable statements. Like, it's more that's more like philosophy. No, sorry, not to I'm not trying to, dunk on philosophy, at all. Philosophy is extremely important. I mean, it's more like speculation and, without evidence, and not I'm not even saying that's necessarily bad. I think what I'm about to describe is I think an experience that every scientist goes through very frequently, which is you have a discovery, you write a paper, and in the paper you put some more stuff than you probably should, like some speculative stuff.
Yeah.
And, because you're testing the waters, you wanna know what the community will sort of respond to. And then you go through the refereeing process and you get multiple experts in your field, and what always happens is they help burn off the stuff that you can't be sure about, and they're left with the sort of thing that is closest to the truth. And, when the process is working correctly. Um, and that's, like, how we should do science. I think if anybody reasonable sort of ask themselves, like, "How do I advance what we consider knowledge?" It would be making statements that are as accurate as possible, and accuracy only comes through sort of this evidence. And so when you're talking about making statements that are fundamentally disprovable, therefore they cannot have evidence associated with them. Like they're not even worth entertaining, of some, not because the idea isn't interesting. Like it's not a serious sort of hypothesis, and therefore it should be left at that. Like it's just an idea.
Yeah, I agree. I agree. And I have this discussion with Benjamin, my 17-year-old, quite often, where we'll talk about something, and it could be something like this, like so the sort of alien comet from interstellar space, and he'll say, "Well, what if it's this, and what if it's that, and what if it's this?" And I'll say, "But Benjamin, what happens if it isn't that? Like you could have, and he will. He's a clever guy. He'll come up with 10 what ifs." And the only what if I come back at him with is, "What if it isn't?" And so you could have a million what ifs, but as long as you've got that idea in your head that, well, what if it isn't one or any of those things, you end up with a null hypothesis of, "I don't know." And a classic sort of demonstration of this has been with this very object, and I've sort of done a bit of research on this as you have over the last few days, is the fact that there was this dust cloud surrounding the nucleus, and it was a bit anomalous. It wasn't easy to explain, and some members in the community said, "Well, the object produced a dust cloud to hide itself." But the language was very odd to me because it was saying it sort of gave either human or intelligent abilities to for this object to give itself a dust cloud to hide itself. And my immediate thought was, what happens if it didn't give itself a dust cloud? It isn't trying to hide itself. The object did produce some excess dust. I think there's no doubt about that. But we have no idea at the moment. There isn't a good model of how that came about. If there's a physical model in the next year or two of how that came about, it doesn't have to have an it. It doesn't have to be deliberate. It wasn't deliberately trying to say, hide, shroud itself from human eyes. And so I think that's the thing I want to be really careful about is if somebody stops me on the street tomorrow with a hot chocolate and says, "Hey, you talked about that alien object, wasn't it cool?" And I'm like, "Yeah, I was trying to give the impression that we didn't know enough about it to say it was an alien object. It just had some interesting characteristics." I won't say it gave itself a dust cloud or it behaved in such a way as to make it appear that it was an alien extraterrestrial civilization or technology. It's a case of, yeah, that object has some really interesting physical characteristics. You look at it through a telescope. Oh, that's interesting. The very fact you can't immediately explain it, my mind, and I think you're the same here, a lot of serious scientists, our minds don't jump to, ooh, it could be this. I think that's what we have to get out there into the general public appreciation of science is sensationalism is really exciting. It gets you YouTube clicks, it gets you on the news, and it is fun, I'll be honest, but it's not rigorous and it's not provable. And you and we've done this for our entire careers. You have to be honest and hold your hand up and sometimes and say, I really wish it was what I thought it was, but really, hand on heart, I need to do some more research and find out what's going on.
And there's never any shame in that to just say, like, "Oh, you don't know enough." And, um, just because there isn't, enough evidence to make a claim does not mean all claims are sort of uh, equally
Yeah.
valid, and there is a process, like, um, and that yeah, there's a reasonable process.
Yeah, I agree, and I mean, I suspect we're drawing to the end here, and if this is sort of us just musing, and we could go all night on this and just talk about how wonderful science is that you get the privilege of asking, Neil.
Yeah, I'm actually I'm a little worried that we're coming across as, like, we're trying to say, like, "Oh, we have to be boring," and, that's the opposite. It's like, every day I wake up, like, so my PhD is funded partially on a National Science Foundation graduate research fellowship, which is from your tax dollars, and, like, that is a privilege that I am incredibly grateful for, and I'm, like, something that I carry with me. When I sit down, I'm like, "I want to make a meaningful result." It's like, I want to do good work with, sort of this blessing that I have been given by the people of the United States, and, that means I want to get you so I wanna get you a result that's gonna last 500 years. That's what my old advisor used to tell me, and, like, um, that means, that is what you want. If you really wanna start doing science and you want to add to knowledge, knowledge isn't a guess that gets proven wrong in a week. It is something that we could take and form and add to our body of humanity's understanding of the universe, and, that's hard to do, and, but it's a great, great privilege that we're all very, very happy that we have.
Yeah, and it's not, I don't think it's actually boring. I agree, I mean, some parts of this podcast and some of our other podcasts, we've come across as serious, and anyone who watches us know that we joke around and we love this stuff. But the serious part is we are professional scientists. And so we've spent our entire lives essentially from when we were 5, 6 onwards, thinking deeply about things, but not rushing to the conclusion of, oh, wouldn't it be great if it was little green men? Like, actually, it would. It'd be bloody amazing. I better ask the questions: is that likely, and is it sensible? And moreover, do the data support that? And I think that's where maybe the boring part comes in. You have to do the boring bit of, yeah, I really wish that spectrum did show me aliens, and God, it'd be amazing. And let's face it, you and I would be as excited as anyone.
Yes, I would be so happy about that. There's not a single scientist on the planet that would be,
That'd be
"Oh,
amazing.
we discovered aliens, but I'm mad because I didn't think it was aliens."
Yeah, yeah. I mean, don't forget. I think all scientists are humans too, right? They have the same innate curiosity and a little bit of sensationalism, right? We'd love to think of did aliens, build the pyramids, or did they seed humanity on here by bringing DNA on a big comet that hit the Earth 5,000 years ago, or whatever it is? Yeah, we'd love some of that to be true. Like, oh, thank God the movies are correct, right? Then just the fact that how we've grown up and how we approach life is, I mean, I think you're the same as me. You go into the garden and you see a caterpillar and you think, oh, I wonder what that wonder what species it is. I wonder what it eats. I wonder how long it lives. I wonder when it's going to become a butterfly. And you ask those questions and you start thinking, oh, I don't know. I'll either look it up in a book, or if not, oh, I'll go and do some research on it. And you look at that caterpillar for 3 months, and lo and behold, it turns into a butterfly. It'd be so easy in this case just to say, "Oh, yeah, the aliens have finally visited us." Is it done ever does it do everything it should do gravitationally in the solar system? No, no. Must be aliens.
This is actually a phenomenal the caterpillar analogy is so good because it's like going into your backyard and then seeing 3 caterpillars, 2 of which are similar and then one of which is
Yes.
kinda different and going, "This is clearly an alien caterpillar," and not being like, "I probably need to look at hundreds more caterpillars in my backyard before I can decide what's weird and what isn't." I really like the caterpillar in your backyard analogy.
Yeah, well, I mean, you could also sort of, be really sort of childish about this and think you were, as cave people sitting around a fire, and your cave wife gave birth to 2 boys. If she gave birth to a girl after that, it's like, "Oh my
Oh,
god,
it's anomalous.
it's anomalous, it's a different species, oh my god." It's like, "No, it's just different from the first 2. Not better, not worse, just perhaps more interesting, but it doesn't make it anomalous."
It's like like I said, the proof by induction fallacy where it's like, well, 3, 5, 7, are all odd numbers, and they're also all prime. So all odd numbers are prime. It's kind of like the opposite of that. Like, and then you get 9, and it's like, oh, 9 is a odd number that isn't prime. Aliens?
Yeah, that's yeah. I think part of it is as well social. I think it's the sort of social zeitgeist is that certainly the last sort of 50, 80 years, of course, with all the wonderful sci-fi out there, it's very natural to think about and exciting that we could be visited by extraterrestrials and that we're so important they're going to come and see us. And
Anybody that says that isn't fun is lying.
it is fun, of course, it's fun.
It's awesome.
Yeah. But so I think so. Here's maybe my last thoughts on this. If you ask me as an astrophysicist what I think of this object, I will talk about everything that we've talked about in this podcast. If you ask me as a 7-year-old boy who loves astronomy and science, but loves Star Wars and loves sort of life, God, wouldn't it be bloody great if it was Darth Vader coming to see us in his little spacecraft? Oh my God, yes. So, all scientists are members of the community as well. Of course, we love the sensationalism, a very hard word to say apparently. We love the idea of it, but then our scientific brain kicks in and thinks, "Oh, I wonder if that's true. I wonder if such and such happened. I wonder if the fact it's from a different star system, not our solar system, makes a difference. I wonder if its orbital period makes a difference." And then you once you start asking these questions, I think unfortunately perhaps that veil of childlike excitement gets dropped, and then you think, "Oh, okay, it's probably not aliens now because some sensible scientific inferences are coming."
I love that. I think, the last thing I'd say as well is maybe a message to our audience, all 5 of them. Sorry. All 4, I didn't count. I was counting out. So, like, especially, and I wanna say something especially to the people who are engaging in the alien sort of hypothesis here. Thank you. Like, and please don't stop, like, doing that and having fun with it and engaging in this, awesome, like, speculation, because it is from your and excitements and enthusiasm and enjoyments that, first of all, it reminds us that we're like, how fun it is to do this stuff, and second, it's also, like, where we get our best, our ideas and our greatest inspiration from you guys, like, from humanity as a whole, and the things that excite us and keep us up at night and what we want to be true, and, um, and thank you for giving us the privilege to try and discern the truth, as
Absolutely.
best as we can. And even though it's not always the fun thing, thank you for giving us that privilege to try to do this wonderful job that we call science.
Yeah. I will say, Joseph, you make a great point in that almost everything we do, not everything, but close, almost everything we do as scientists these days is either funded through the public domain or private foundations.
Yeah.
Obviously, the private foundations are slightly different because that's set up with donations and bequeathments. But all the public money we receive, almost every image you showed tonight was generated by
NASA or ESO.
NASA or ESO or the old VLTs or ESO is funded by public taxpayers, including us, right? We pay taxes too. It's
We
funded
do?
by public. Well, yeah, I probably pay a bit. Amount of tax I pay seems ridiculous, but there you go.
I'm a student. I don't have to pay taxes, right?
You don't pay tax? Oh, maybe you should. Should admit that in public. There.
That was a joke for the IRS.
Oh, the IRS
Joke.
thing. That's right.
I pay my
I think that's really important for us to remember is an awful, as you said, the privilege of what we do is that it is publicly funded, and that's somewhat of the reason why you and I started doing these podcasts is we wanted to give something back.
Yes.
All our education, most of it was funded by the public as well. So it's just, hey, we owe you this.
There's a valid argument to this that I'm seeing, being surfaced right now, which is, like, scientists have their own ideas about Terra Atlas, but there's a frustrating sort of lack of communication between what is happening and what people are hearing. And, like, that was a lot, like you said, that's what a large part of why we wanted to do this is, unfortunately, there's this thing that occurs, which is when you're a scientist doing science, you don't have a ton of time to, like, engage in communication as much as you should. And so that's why we're making this effort to say, like, we're science and we're doing scientists. Sorry, we're scientists. we're not doing science. We're scientists and we're doing science.
Yeah.
And as which is why we can't put out an episode necessarily every week because we're actually going and doing science and sitting on telescopes and writing papers and applying for grants and stuff. But like we want to as much as possible like share this with you and not just have this be hidden behind this veil of like elitism or you know a puffery like about our yeah. It's a privilege that we are humble and grateful for.
We are very grateful, and I love the fact. Actually, I love what you just said, and I was sort of rambling on a little bit here, but like a lot of the questions you and I put to each other tonight were submitted to us by my friends Iz and Nora. These two young people who adore science. They want to be scientists themselves. They fit, you know, when I engaged them and I went to their school and I went to visit them and we talked science for days and they asked them those beautiful questions. These two beautiful souls on this planet just were so like it just they reminded me of me at 7. They just loved the idea of talking science and thinking, oh, what if? Or why does that happen? Or hey, that shouldn't happen. This happen? Again, they are part of the or a big part of the reason why we do this is we love talking about science to the community and getting people interested in this stuff. It's amazing.
When I see the comments in the like on the videos where it's like people are just so amped up and they have those really creative questions that like we either have gotten so used to we don't even think about or are just so far out of left field that it's like we get this opportunity to talk about this thing we never even think about. Like it's
Yeah.
like the greatest. Is that a picture of 7-year-old you behind?
No, that's a. I don't think I was quite 7. I was actually very short up until I was about 17. That's my
Ultimately, you were approximately 7.
approximately 7. I was approximately 40-ish.
Okay. Wow. 40 for real?
I think so. Yeah, it's taken
You
about 15.
consistently look like 20 years younger than you actually are.
I don't think I'm 55 and I look 55. So I've got the grey beard, the grey
Uh,
hair.
you look like a young man, David. Speaking of what you look like, tell us about the shirt.
Oh yeah, this is a great shirt I got from an old girlfriend, and she bought me this for Christmas, and it is a Star Wars Christmas shirt. I can show you a bit of it. If I do it too much, the green screen will take over. But there's this the green screen.
We lost it. There you
Yep.
go.
There you go. There's an X-wing with the Ally fighter being zapped. There's a big X-wing here, and I think you all know by now I'm a pretty big Star Wars geek. So
That's awesome. I love it. Well, I think you want to bring it to a close, David?
I think so. Thank you, Joseph. This has been a lot of fun and a complete privilege as always. Thank you for your
Ditto.
work and happy holidays to you, my friend.
You too, right? Great to see you.
Great to see you too. And we've both been busy, but we're going to get more done in 2026. I promise.
That's the plan. Okay,
I
thanks,
love you,
everyone.
brother.
Love you too.
Well, this wraps up another presentation for Astraveo, where we go from geek to chic by sharing our passion and excitement for all things scientific, especially astronomy and in the mysteries of the universe. If you enjoyed this video, please hit the like button, and in the comments below, please leave us your suggestions for future presentations. We'll get right on it. And don't forget, you can join us on our journey by subscribing and hitting that bell. He's Joseph, and I'm David, and together we're Astraveo. Thanks for watching.